Continuing with Packet2 and limits. In this example, we are taking the limit as h goes to 0. So we do need to do some simplifying since having h on the bottom isn't good. Hopefully it simplifies. Phew! H canceled out. Nice. Another example. Looks very similar to the previous example, right? So we do the same thing, simplify, and hopefully h cancels out. And done. P.S. You don't know it, but you just found the derivative of the function y equals x cubed. Here are a couple more limit laws that may be useful. A couple of examples using the laws above. By now, you may be noticing that for most of our functions, when we take the limit, it seems we can just plug a into our function. And that is a property as well. There are more functions that follow the direct substitution property, not just polynomials and rational functions. In conjunction with the limit laws, a lot of limits simplify to a polynomial or a rational function. Another limit example. Here we recall what the absolute value function is and looks like. Since we're looking for the limit as x goes to 0, we need to look at it from the left and right. So we set up the two limits, remembering when x is greater than 0, we take the limit of x. And for x less than 0, we take the limit of negative x. Since both limits are equal, we know that the limit of the absolute value of x as x goes to 0 will be 0. Another example. Similar to the previous example, we need to set up two limits going from the left and right side of 0. Notice the two limits are not the same. Therefore, the limit does not exist. Here we see a couple of theorems for comparing limits of functions. The first theorem just says if a function g of x is larger than a function f of x, then the same goes for their limits as x goes to a. The squeeze theorem says if you know that g of x is larger than f of x and smaller than h of x, and if we know that the limits of f of x and h of x as x goes to a are equal, then the limit of g of x as x goes to a has to be equal as well. Let's look at an example. We will call this g of x. Looking at the sine function, we know that it fluctuates between 1 and negative 1. So we basically know we can compare this function we call g of x will be between the two functions negative x squared and x squared. We will call the left function f of x and the right one h of x. Let's also take a peek at what this looks like on the graph. Kinda cool, huh? As you can see, the function g of x definitely is between the two functions f of x and h of x. So now if we look at the limit of f of x, g of x, and h of x, we find the limit of f of x as x goes to 0 is the same as the limit of h of x as x goes to 0. And this means, by the squeeze theorem, we know that the limit of g of x is 0. Going back to the graph, we can see this result as well. Another example, very similar process as the previous example. We call the function we want the limit of g of x. We know sign fluctuates between -1 and 1. So we know that g of x will be between the two functions written here. We will call them f of x and h of x. Let's look at what this looks like on the graph. And we can see that g of x is definitely between f of x and h of x. So taking the limit of f of x, g of x, and h of x as x goes to 0, we see that the limit of f of x and h of x as x goes to 0 are both equal to 0. So in turn, the limit of g of x as x goes to 0 must also be 0. Now we will try and examine a curve and try and figure out how we can find the rate of that curve at any point on the graph. So if we label 2 points P and Q as we see on this graph, we know we can find the rate or slope of those 2 points. This line is called the secant line since it hits 2 points on the curve. Now let's label the corresponding x and y values. In general, we want h to be really small. I'm not making it look small here because we want to get the general idea first. If you think about it though, if h was super small, like almost 0, then the line would look like this. This line is called a tangent line because it's the line that hits the edge of the curve and the point P. We can draw another tangent line through Q. In general, if we can find the tangent line of a curve at a certain point, then we know the rate or slope of the curve at that point, which is exactly what we want. Before we can do this though, we need to start with the secant line. So recall how to find the slope of a line with 2 points. We also introduce a notation that means change in x and change in y. We say it as delta x and delta y, which means change in x and change in y. So writing the general slope of a secant formula down, which is also average rate of change. We can use what we wrote down above to plug in to the secant line formula, which is just change in y over change in x. And we end up with the difference quotient that you may remember. What's cool about this is that if we take the limit of this difference quotient as h goes to 0, it gives us a way to find the rate / slope of a point on a curve at any point. Awesome, right? So let's look at an example using the average rate of change idea. Keep in mind, each of these examples are just using the algebraic slope formula. The cool stuff comes in the next packet, where we can use calculus to find the rate of a curve at any point, not just the average rate.